All right. The last part of today's lecture will be concerned with model-based meta-reinforcement learning. So far, all of the methods we've talked about have been focusing on the model-free setting. And in many ways, the model-based setting is simpler because many of the same ideas that we use for supervised meta-learning can be applied to meta-trained models. So in model-based meta-RL, very much like in the standard model-based setting, we're going to go from kind of the case where we're concerned with training the policy to the case where we're more concerned with training the model. So we're going to improve our policy implicitly by improving our model from a little bit of experience. So the short sketch of model-based RL, this is basically the model-based RL algorithms that we learned about before. Collect some data, use that data to get your approximate model, p hat of st plus 1 given st at, and then use that model, in this case, to plan A. And these ideas could be applied to model-based RL algorithms that learn policies as well, but for now we'll just be concerned about model-based RL algorithms where we only learn a model and then perform planning. So why might we want to do this? Well, it can require much less data than model-free methods, particularly doing meta-training, because model-free meta-RL algorithms might be very efficient at adapting, but they might still be very expensive for the meta-training phase, and using models can alleviate that. Now, there are some differences in how this is performed because of the presence of the model, and the other fact, though, is that model-based meta-RL algorithms can in principle also adapt extremely quickly. The reason for that is that model-free meta-RL methods ultimately adapt by observing rewards, whereas a model-based meta-RL algorithm could adapt simply by observing model misprediction. So before it even sees what reward it's getting, just from seeing whether it's predicting the next states accurately or not, it can immediately change the model. Okay, so here's an example of a potential task or potential situation in which we might want model-based meta-RL to adapt, in this case where the task changes within a single episode. So let's say that you have this ant, and partway through the episode, one of the legs becomes broken, so that's shown in red. Now, the gait that you learned with 4 legs is not going to work anymore because you only have 3 functional legs left. But if you could quickly adapt your model, then you could use the adapted model to walk successfully. So a non-adaptive method would collect data, collect a few episodes, train the model, something that predicts S prime from S and A, and then use the model to optimize the actions, right? And you would choose the actions, for example, with planning. An adaptive method would take a step and observe S, A, and S prime. It would update the model somehow, for example, by using a model-agnostic meta-learning or an RN approach, whichever you prefer, and then use the adapted model to optimize the actions. And you could adapt the model even every single time step if you like. Now, of course, if you don't actually do any meta-training, if you just take these gradient steps naively, that's a nice idea, but how much can you really adapt in just one step? Right? So without meta-training, this adaptive approach doesn't really work with deep nets. It can actually work with very simple models, such as linear models, and the entire field of adaptive control is basically concerned with this problem. But if you have a deep neural network model, you can't really adapt all that much from just one sample. But with meta-learning, you could. So at meta-test time, we're going to have this adaptive procedure, but at meta-training time, we'll actually construct a meta-training set, just like in the supervised learning case, just like in that Ravi and La Rochelle picture at the beginning of the lecture, consisting of multiple training sets and test sets. And the question that we have to answer is, how do we construct this meta-training set? Because once we construct it, we can basically use any supervised meta-learning algorithm to perform this meta-training, including model-agnostic meta-learning or an RNN approach or whatever else we want, and then just use that for adaptation at meta-test time. So the only thing that we really have to figure out to do model-based meta-RL is how to construct the meta-training sets. And the meta-training set, remember, consists of a set of training test set tuples. And we're going to meta-train by adapting on DI train and then updating our adaptation procedure so that the post-adaptation, so the phi i's, do well on DI test. Okay, so our x here is s comma a, our y is s prime. So we can generate each DI train and DI test as following. we're going to sample some subsequence, st through st plus k, from our past experience. And this assumes that our past experience consists of many different dynamics. So maybe in the past we saw different legs break and we saw different terrains and so on. We don't know when we saw them. We don't even need task boundaries for this, but we'll just sample these subsequences randomly. And then we'll say that dtrain is the portion of the subsequence from st to st plus k minus 1. You could choose k equals 1, but k greater than 1 works a little better, so let's say that k is around 5. And dtest is that last time step. So dtest is the transition st plus k, at plus k, st plus k plus 1. So the idea is that you adapt to st through st plus k minus 1, and then you try to do well on st plus k from that adapted model. So if you have some long trajectory, you're going to choose a chunk of that trajectory to be dtrain, and the chunk right after to be dtest. And if we do this, this is actually quite nice because it's representative of what we'll see at meta-test time. At meta-test time, we'll get one or more steps, and then we'll be required to do well in the next step. So this procedure actually constructs these dtrain, dtest tuples in the way that is most analogous to what we'll see at meta-test time. So then when we use this for meta-training, we end up getting good results at meta-test time. So here is the task with a broken leg, but now with a model that has been meta-trained, you can see as soon as the leg breaks, it actually changes the gait immediately. You don't even notice how long it takes to adapt because the adaptation is virtually instantaneous with model-based MetaRL. Here's the same idea used for real-world robotics tasks. So this is a hexapod robot developed here at UC Berkeley by Professor Ron Fearing's group. And there are a number of perturbations here. We're going to see different terrains. So the meta-training just consists of collecting data from different terrains, which already provides enough variability. And then at meta-test time, we'll perturb it in other ways. So here, one of the legs was removed. Now, we never saw a removed leg, but we saw a variety of different terrains, which is enough to sort of exercise the different modes. And on the picture on the right, the goal of the robot is to keep as close to the center line as possible. And you can see that the adaptive method, which is the one on the right, does the best. Here it's placed on a slippery slope. And again, the goal is to stay close to that blue center line. You can see the adaptive method on the right mostly manages to do that. This is simulating a sensor miscalibration and so on. So hopefully you get the idea at this point. And there are a number of other papers you could check out on this topic. I wanted to briefly show this video. This is kind of a more recent work showing model-based MetaRL for a quadrotor task. So here this quadrotor is using a magnetic gripper to pick up a payload, and then it's supposed to get that payload to follow some desired trajectory in image space. So here it's supposed to trace out a square. So the reason that meta-learning is important for this task is when you pick up a payload with a magnetic gripper, the weight of the payload changes and the length of the tether changes. And the quadrotor needs to adapt to both of those things to maintain stable flight. So this is kind of a prior method that doesn't really do so well. And here is the model-based MetaRL. And this model-based MetaRL method actually uses some probabilistic variational inference ideas in addition to the adaptation procedure that I discussed before. All right. To conclude, one of the last things I want to do at the end of this lecture is to also briefly discuss a few other works that have looked at MetaRL through the lens of kind of cognitive science and emergent phenomena. This is not really related to the model-based part, but it's just kind of an interesting side note for those of you that are interested in this topic. So besides just developing better MetaRL algorithms, one of the things that people have done in the research community is study how MetaRL can account for the natural emergence of various higher-level concepts. For instance, one known property about human-animal learning is that humans and animals seemingly learn behavior in a variety of ways. Highly efficient but apparently model-free RL, episodic recall, and model-based RL. And a lot of folks think that these are maybe just different learning mechanisms that are all embedded in the brain. Causal inference also seems to play a role, and so on. So, probably the dominant hypothesis in cognitive science and psychology is that each of these might be sort of a separate algorithm that's implemented in the brain. But what if these are all emergent phenomena that result from MetaRL? This is an intriguing hypothesis, not by any means a fully validated one, but quite a few papers have studied this. For example, there's a paper that looks at how meta-RL can give rise to episodic learning, episodic recall, which is typically considered kind of a separate mechanism, but this paper shows that model-free meta-RL can result in episodic recall. There's a paper that shows that model-free meta-RL can give rise to model-based adaptation. So the hypothesis that this paper makes, which I don't know if this is true or not, but it's an interesting hypothesis, that model-based reasoning actually emerges as a consequence of model-free meta-learning. There's even a paper that looks at whether meta-RL can give rise to causal reasoning. So if you're interested in some of these topics, I would encourage you to check out these papers.